The original goal was routine. Track 3I Atlas as it approached its mid-December transit. The object had already defied expectations by maintaining a stable brightness, and its movement had drawn amateur astronomers into near-continuous coverage. One of them, a retired systems engineer named Daniel Rivas, had logged more than 60 hours of footage across multiple nights. On this particular run, he aimed to capture extended long exposure frames to document Atlas's tail behavior during its current solar alignment. He didn't find a tail. What he found was something else, something just outside the main nucleus of Atlas. It was faint, barely more than a glimmer on the edge of the CCD. At first, it looked like background noise, a star reflection, maybe a lens artifact, but it moved, not randomly, not like a meteor streaking through frame. It moved with the arc, with Atlas. Frame by frame, the faint point traced the same trajectory, but at a very slight offset, not in front, not behind, beside it, always on the same side, and when Rivas stacked the frames and overlaid the motion vectors, it became undeniable. This wasn't a glitch, it wasn't a camera problem, it was a second object, smaller, dimmer, but real. He reran the footage through his pipeline, swapped filters, reprocessed with noise reduction off. The anomaly remained. He posted the findings to a private forum of deep sky observers. Within 4 hours, 2 others had matched his results, one in Utah, another in southern Australia. Different hemispheres, different equipment, same anomaly. That's when the flags started going up. On December 12th at 0712 UTC, the Minor Planet Center issued a preliminary observation note, not confirming a second body, but noting a recurring signal with correlated vector motion. In plainer terms, something was moving with Atlas, and it wasn't debris. The confirmation came just hours later when a team from the Las Cumbres Observatory Network conducted a rapid follow-up. Using time-synchronized scopes in Hawaii and South Africa, they captured simultaneous multi-angle footage of the same sector. The second object was visible from both locations. It wasn't a shadow, it wasn't reflected dust. It had a defined motion vector, matching Atlas within less than 0.2 degrees of angular drift. And it wasn't falling behind. If anything, it was adapting, subtly accelerating and decelerating in ways that ruled out gravitational coincidence. For analysts reviewing the footage, the implications began to sharpen. This wasn't a fragment. It wasn't the result of an earlier outburst or breakup event. The spacing was too clean, the motion too controlled, and most important, the second object didn't tumble. It didn't rotate. It maintained orientation over multiple observations, locked like it was following a path, not simply obeying one. Within 24 hours, the object was unofficially designated as a formation companion in Analyst. Circles, not a satellite, not a splinter, a twin. And once the large observatories reoriented, they saw it too. That's when the questions began to shift, from what it was to why it was there. Because the deeper you looked at it, the more it resembled a shadow. Not cast by Atlas, but following in its wake. Not accidental, not natural. And whatever it was, it saw us before we ever saw it. The twin wasn't drifting. That became clear within hours of the first confirmation. While most comet fragments tend to behave erratically, spinning, trailing and decaying, the object trailing Atlas showed none of that. Its path was deliberate, not loosely bound by gravity, not chaotic. It moved with precision, locked into something no comet debris had ever shown: coordinated orbital intent. The first detailed trajectory overlays came from the Canadian Institute for Space Tracking, using data captured by the Mount Lemmon survey in Arizona and the Pan-STARRS facility in Hawaii. Analysts plotted the position of both 3I Atlas and the newly identified companion across 84 minutes of synchronized telescope footage. The results were immediate. Angular momentum between the two was not only similar, it was synchronized. Not identical, but close enough to suggest something deeper than coincidence. The slight differences in arc curvature weren't random. They were reactive. Every minor shift in Atlas's velocity or tilt was echoed by the twin with delay, a precise delay. Initial models showed a latency of just over 7 seconds between Atlas's adjustments and the twin's compensatory moves. That alone ruled out natural orbital coupling. Comets don't synchronize, fragments don't follow, and yet the formation held, like choreography. At ESA's mission control, orbital analysts ran predictive simulations. When they plotted the twins' path using standard gravitational modelling, it failed within 2 revolutions. The object's movement diverged from every known ballistic pathway. It wasn't just moving through space, it was adjusting, correcting, countering drift with micro-movements that couldn't be explained by solar radiation or outgassing jets. Then came the spectral comparison. Using infrared and visible light spectrography from the European Southern Observatory, scientists analysed both objects across 4 distinct bands. The data showed overlap in reflectivity and thermal profile. Both had high albedo values, suggesting smooth, possibly reflective surfaces, but the twins' values were cleaner, more uniform, less disrupted by dust or surface decay. That difference mattered. 3i Atlas still carried traces of volatile shedding. Not much, but enough to imply surface activity. The twin did not. Its spectrum was quiet, flat, almost cold. It wasn't venting, it wasn't shedding mass, and it wasn't heating, despite being under the same solar intensity as its counterpart. It also showed no coma. Where Atlas displayed faint traces of a tail and sublimated trail, the twin remained sterile, a line in motion, no blur, no diffusion. Even at maximum zoom, the profile held rigid. NASA's trajectory analysis team ran the motion data again. What they found disturbed them. At exactly 8:44 UTC on December 12th, both Atlas and the twin made a minor trajectory shift, barely more than a fraction of a degree. Atlas led. 7 seconds later, the twin followed. But the magnitude of the shift was slightly cleaner, smoother. The twin moved as if guided. This created a new modelling problem. If the 2 objects were gravitationally independent, they shouldn't be able to maintain such tight formation. If they were gravitationally linked, they should show signs of mutual influence, wobble, lag, orbit. They showed none of that. Instead, they acted like 2 points following the same invisible track, a mirrored path, echoing but not overlapping. It wasn't tethered motion, it was paired navigation. Further analysis revealed one more anomaly. During moments when Atlas's velocity temporarily spiked, presumably from minor outgassing events, the twin maintained its speed, then compensated. It didn't simply mimic, it recalculated. That term kept appearing in internal reports, recalculated, as if it had a model of Atlas's trajectory, as if it was watching and adjusting to match. By the end of the day, trajectory correlation was confirmed to over 98.4% in angular motion. In astronomical terms, that's not coincidence, that's control. And in that control, the question evolved again, because now it wasn't just about what the twin was following, it was about what it was responding to, and why. Symmetry is rare in nature, especially in motion. Even in the most stable orbital systems, perfect alignment decays over time. Gravitational tugs, solar wind, thermal irregularities all introduce drift. Comets are especially prone to this. Their surfaces are uneven, their cores fractured, and their reactions to solar heat unpredictable. They wobble, they vent asymmetrically, they spin and scatter and change shape. That's what makes them comets. But this wasn't that. From the first composite overlays taken by the Solar Dynamics group, it became clear 3i Atlas and the twin were locked in something far more precise than any natural formation should allow. Not just matching trajectory, matching rhythm, matching distance, matching angular alignment, perfect symmetry. Over the course of 11 hours, 39 high-resolution frames taken from observatories across 3 continents were run through differential comparison. Analysts expected to see deviation, a widening arc, an increasing drift, perhaps signs of inertial lag between the 2 objects. They saw none. The distance between them remained constant to within less than a kilometre. Across thousands of kilometres travelled, neither object shifted out of formation. When one turned, the other mirrored. When one dipped, the other followed. When one accelerated, the other corrected. But that wasn't the anomaly. The anomaly was what happened at 14:03 UTC. For exactly 2 minutes and 21 seconds, the twin accelerated past Atlas. Not violently, not randomly, smoothly. A slow increase in velocity measured at just under 1.3 meters per second, enough to pull ahead of Atlas by nearly 8 kilometers. And then it stopped. it fell back into formation. No cause, no outburst, no thermal spike, no visible propulsion, just motion, then stillness. The kind of maneuver that cannot be explained by ice sublimation or cometary jets. That kind of coordinated speed change requires timing, awareness, a feedback loop. Analysts at the Max Planck Institute described it as a controlled surge. But comets don't surge, they fragment, they flare, they react. This didn't look like reaction. It looked like choreography, and symmetry was the result. Further spectral comparison deepened the mystery. As the twin passed momentarily ahead of Atlas, its reflective curve remained unchanged. No surface rotation, no tumbling, no shading effects from orientation shift. The light stayed constant, like it was locked in a fixed attitude. That's not how natural bodies behave. Every known interstellar object, from Oumuamua to Borisov, has shown at least some spin. Most have irregular rotation curves. Even our own solar system's comets have axes that drift over time. Yet the twin held its orientation as it passed, as though facing forward, intentionally, as though it wasn't just symmetrical in position, it was symmetrical in behavior. NASA's Deep Space Network tried to model the formation using passive dynamics. Their simulations broke apart within 6 iterations. The formation only held when control variables were introduced, parameters for guidance, correction, and stabilization, words usually reserved for spacecraft, not ice, not rock, and certainly not comets. One internal report posed the question directly. If this is natural, what force is maintaining the symmetry? There was no answer, because symmetry by itself isn't proof, but when symmetry holds through motion, when it resists chaos, when it adapts mid-course and returns to equilibrium with no visible tether or trigger, that's no longer nature, that's a decision, and someone or something is making it. Light behaves predictably in space. It travels in straight lines. It reflects off surfaces based on angle, material, and texture. Astronomers can read its behavior to measure distance, temperature, composition. From the faint flicker of a star, they can infer an entire planet. From a comet's brightness, they can detect the chemistry of vaporized ice. Light doesn't lie. But sometimes it answers a question no one thought to ask. On December 12th, at exactly 4:13 UTC, 3 separate observatories, 2 ground-based in Chile and 1 in La Palma, recorded something they could not immediately explain. A reflective spike lasting less than 4 seconds, coming from both 3I Atlas and the object trailing it. Not a flare, not a gas jet, not a lens artifact, a pulse. It was sharp, clean, focused in the visible band, not thermal, not infrared, just a sudden increase in reflected sunlight, not emitted light, but returned, and that detail mattered, because what followed wasn't just strange, it was synchronized. Across all 3 recordings, the pulse emerged first from Atlas, and then, less than half a second later, from the twin. A staggered flicker. Identical intensity, same spectral profile. A mirror image delayed by milliseconds, like a signal bouncing between 2 points. Initial theories suggested surface rotation, a smooth face catching the sun at the right moment. But that would require both objects to spin in perfect coordination, same axis, same timing, same orientation to the sun. They weren't spinning. Both objects, confirmed by photometric flatness, were locked in their attitude. There was no observed change in angle, no shift in shadow, yet the light increased and dropped, as if something on their surfaces had momentarily changed. Not the position, the reflectivity. This wasn't emission, it was reflection. But not the kind comets typically produce. Icy surfaces scatter light. Dust particles diffuse it. Reflected brightness in comets comes in smudges, glows, and tails. Never a clean directional flash. And never from 2 bodies, moving together. The Chilean team at Cerro Tololo called it a specular reflection event. But even that term fell short. Specular reflection, like the flash from a mirror, requires a smooth surface and a precise angle. But these objects weren't aligned toward Earth. The pulses occurred while both bodies were roughly 14 degrees off-axis from direct observation. In those conditions, standard reflective theory says no flash should have reached us. Yet it did. Further analysis showed something even stranger. The reflected pulse was not uniform across wavelengths. It favoured the yellow-green band with a sharp drop-off above 650 nanometers. That's not a solar flare artifact, that's surface selectivity. Materials that reflect in that way tend to be engineered, coated, optimized, not natural. Spectral models run through the ESA's Strater lab suggested a highly directional albedo event, one that could only be caused by a surface with adjustable reflectance properties, either through geometric reorientation or through material phase change. Neither option exists in any known cometary model. Then came the follow-up. 2 hours later, another flash. Fainter, shorter. And again, both objects responded. Atlas first, the twin second. The delay was the same. The timing was precise. The pattern repeated. That's when the team at Palomar Observatory released their internal memo. We may be observing the optical equivalent of a handshake. It was a phrase that spread quickly through the astrophysics community, not because it proved anything, but because it described something deeper, a rhythm, a repeatable behaviour, a communication not in words but in light. And still, nothing followed. No radio signature, no infrared bloom, no high-energy echo. Just the quiet certainty that somewhere in space, two objects, one known, one unknown, had exchanged a flash of light. Not by accident, not by physics, but by intent. Light doesn't just reflect, it polarizes. When sunlight bounces off a surface, be it gas, dust, ice or metal, it shifts. The angle and structure of that surface determine how the light's electric field becomes aligned. That alignment, known as polarization, acts like a fingerprint. It's subtle, invisible to the eye, but unmistakable in data. Astronomers use it to study surface texture, particle size, and material composition. Comets have their own signature. So do asteroids. Even gas clouds leave behind polarization curves that can be mapped, measured, understood. But the polarization recorded from 3i Atlas and its twin doesn't fit any known category. The first data came from a team at the European Southern Observatory using their polarimetric imaging system on the Very Large Telescope. Their goal was simple: monitor how light scattered off Atlas's surface as it approached Earth's orbital plane. The assumption was that Atlas would behave like a standard interstellar comet, show signs of asymmetric polarization caused by ice particles and venting dust. That's not what they found. Instead, they captured a deep negative polarization curve, a value of negative 2.9% at a phase angle of just under 15 degrees. That alone wasn't alarming. Some comets do show brief negative curves, but then they aimed at the twin, and it matched, almost exactly. Same depth, same angle, same wavelength sensitivity. Two objects moving in formation, reflecting polarized light in a near-identical pattern. No other cometary pair in modern astronomical history has produced anything like it. That was the first clue. The second came when the team plotted the inversion point, the angle at which the polarization switches from negative to positive. For most comets, this happens around 20 to 25 degrees. For Atlas and the twin, it happened at 17, consistently, in multiple bands. That's not just a fingerprint, that's a match set. Natural surfaces tend to scatter light irregularly. Dust clouds introduce random diffusion. Ice crystals distort and blur the signal. But these two objects were clean. Their polarization was smooth, consistent, coherent. The signal didn't fluctuate with distance or spin, because, as later confirmed, neither body was spinning. The behavior mimicked that of a solid surface, compact, non-porous, highly structured. But it didn't end there. NASA's Goldstone Solar System radar tried to cross-confirm the findings with independent polarization analysis. Using radar backscatter, they measured the surface, reflectivity response to microwave frequencies. Atlas returned expected values: weak, scattered, indicative of uneven terrain or dust covering. But the twin returned something very different: a coherent return signal, narrow, shaped, with minimal scattering. In polarization terms, it was tight band aligned, something only possible if the surface is smooth, compact, and reflective at a structural level, like metal. The term that appeared in internal documents was specular polarization alignment. It's a mouthful, but what it means is simple. This object doesn't just reflect light, it aligns it. That requires surface geometry, angles, planes, shapes. Natural ice does not do this, nor does porous regolith, carbonaceous dust or loosely held comet material. Only structured surfaces can manipulate light in that way. And yet, there it was. Not once, not briefly, but over 3 consecutive nights, at multiple wavelengths, from multiple observatories. 2 objects, one known, one unknown, reflecting polarized light with matched spectral response. The implications weren't spoken aloud in press briefings. They didn't appear in public memos. But the question hung behind every polarized curve. What kind of object reflects light this precisely? And why are there 2 of them? Spectral signatures don't lie. Every object in space reflects or emits light in a way that reveals its composition. Whether it's the glow of hydrogen in a distant nebula or the frozen carbon dioxide on a comet's shell, the light carries a code. Spread it through a spectrometer, and it breaks into patterns, lines, dips, and peaks that point to specific elements. For scientists, it's the closest thing to reading the DNA of a celestial body. 3i Atlas had a signature: cold, stable, slightly skewed toward the yellow-orange band, consistent with a surface rich in carbon compounds and possibly irradiated ices. The data had been holding steady for weeks, with only minor fluctuations due to solar wind interference. But the twin was different. At first, its spectrum seemed nearly identical to Atlas. Same absorption lines, same slope, same general shape. The early assumption was that the objects shared a similar origin, perhaps fragments of the same body or products of a shared interstellar region. That assumption didn't last long. On December 12th, just after the reflected pulse event, the twin's spectral signature began to shift. Slowly, subtly, but persistently. Wavelength by wavelength, the curve drifted toward blue. That shift was first noticed by the team at the Canada-France-Hawaii telescope, who had been running a continuous sweep across the visible and near-ultraviolet bands. What caught their attention was the change in reflectivity around 430 nanometers, a range typically sensitive to surface frost or fine dust exposure. But this wasn't surface ice sublimating, it was something deeper. As the hours passed, the slope of the twin spectrum increased. The shortwave side, near violet, began to rise in intensity. It wasn't just brightening, it was transforming. Surfaces that reflect more blue light typically become exposed through erosion or shedding. In some cases, it indicates the loss of a top layer, but no dust plume was observed, no coma, no measurable mass loss. The object wasn't losing material, it was revealing something. At the same time, the thermal signature, already weak, flattened completely. Instruments aboard the ESA Solar Observer reported no increase in infrared flux, no heat spike. Whatever was changing, it wasn't reactive. It wasn't chemical, it was controlled. Researchers began modelling the event as a possible surface phase transition. Certain alloys, under solar exposure, can shift their reflectivity properties without increasing in temperature. This has been demonstrated in lab conditions, smart materials that darken or brighten based on radiation load. But no such material has ever been confirmed in a natural body, yet the twin was doing it. It didn't just reflect more blue, it stopped reflecting red. The long-wave tail of its spectrum began to dim, collapsing in slope. That kind of behavior implies selective absorption, a surface rejecting specific wavelengths while amplifying others. That's not erosion, that's tuning. The working theory became harder to ignore. Some kind of metamaterial skin, reactive to solar exposure, was altering the reflectivity of the object in real time. If true, it would mean that the twin didn't just reflect light, it controlled how it reflected it. The gap between Atlas and the twin widened, not in distance but in spectral identity. One held steady, the other evolved. It was as if one object was passive, and the other was adapting. The phrase used in an internal memo from ESA's Optical Science Division said it best. Spectral drift implies behavior, and behavior suggests choice. Outgassing is the heartbeat of a comet. It's what defines them, what makes them glow, evolve, fragment. As they approach the sun, the increase in solar radiation heats their surfaces, ice sublimates, dust escapes, streams of gas erupt into the void, creating tails that stretch for millions of kilometers. It's a chaotic process, uneven, asymmetrical. No 2 comets vent in exactly the same way, but all of them vent. 3i Atlas was expected to do the same, It didn't do much. From the start, Atlas showed unusually low levels of volatile emission, faint water vapor signatures, minimal dust halos, just enough to confirm that it was in some sense behaving like a comet, if barely. Its outgassing was thin, contained, and possibly coming from deeply buried reservoirs rather than a typical icy crust. But the twin showed nothing at all, not even the faintest trace. This wasn't just unusual, it was in direct contradiction to cometary physics. From its distance to the Sun, from its size, from its expected thermal profile, the twin should have been shedding material. But it didn't. Instruments from ESA's solar observer scanned the object across 3 different wavelengths: ultraviolet, infrared, and near visible. All showed a flat line in mass ejection. No coma, no dust, no molecular trails. The background remained perfectly clean. The James Webb Space Telescope followed. Using its mid-infrared instruments, it targeted the twin during its Earth-approaching segment. If even a few molecules of carbon dioxide or water vapor had been released, the sensors would have caught them. They didn't. The result wasn't low activity, it was silence. The twin had no cometary wake, no thermal bloom, no evidence of volatile loss. It moved through space like an inert object, cold, stable, unchanging. Researchers at the University of Arizona's Lunar and Planetary Laboratory tried to replicate the conditions in simulation. They modeled dozens of compositions: icy, rocky, carbon-rich, even exotic volatiles from interstellar chemistry catalogues. All produced outgassing when placed under equivalent solar heating. Except the twin didn't. The problem deepened when spectroscopic arrays from the Mauna Kea Observatory attempted to detect hydroxyl radicals, fragments of water molecules that appear when sunlight breaks them apart. It's the most basic conformation of sublimation. Even dormant comets usually show a trace amount. But from the twin, nothing, even at high exposure, even across multiple days. This led to an uncomfortable question. If the object wasn't shedding gas, what was holding it together? Comets are fragile. Their internal structures are porous, loose collections of rubble held in place by ice and gravity. As they heat, they weaken. Even stable ones show signs of deformation. The twin didn't deform, it didn't flake or tumble, it held shape, rigid and exact. NASA's Near-Earth Object Program issued a short internal bulletin. No volatile markers detected on trailing object. Structural consistency suggests non-porous material. Non-porous. In the language of material science, that's code for solidity. Metallic. Engineered. There were alternative theories, of course. One proposed that the twin had already shed its volatiles during an earlier pass near another star, leaving behind an inert core. But that raised its own question. Why was it still stable? Why was it moving with precision? Why did it show signs of attitude control if it was dead? The absence of outgassing was no longer just an observation. It was a message. The twin wasn't interacting with the sun. It wasn't responding to heat. It wasn't decaying. It was holding position silently, as if the sun didn't matter, as if it had no reason to react. And in space, where every reaction is a clue, no reaction can say everything. There's a difference between movement and response. All objects in space move, pulled by gravity, nudged by light, pushed by pressure, but not all of them respond. Response implies timing, implies intention, implies awareness of something else nearby. 3I Atlas had been under continuous observation for weeks when astronomers noticed something strange, not in its trajectory, but in the way the object behind it moved, the twin. The observation began with a course correction. On December 12th at 1544 UTC, 3I Atlas made a subtle vector shift, the kind of adjustment that, in comets, typically suggests a mild outgassing event, material released asymmetrically from one side of the nucleus, producing a measurable nudge in the object's velocity. Atlas's shift was small, barely noticeable unless you were tracking it in real time, but someone was. 7.2 seconds after Atlas shifted, the twin did too. Not a passive drift, not a gravitational echo, a perfect mirror of the movement, same angle, same distance, same curve. It was like watching a dancer copy a step with slight delay. Except this wasn't performance. This was deep space. And comets don't dance. Analysts at the Jet Propulsion Laboratory ran the telemetry 4 times. They thought it was sensor error, then software misalignment, but the result held. When Atlas shifted, the twin matched it over and over again. They called it a motion echo. At first, the delay was consistent, always 7.2 seconds, but over the next several hours it began to vary, slightly. The delay stretched to 7.9, then dropped to 6.5, then settled back into its original rhythm. These weren't random fluctuations. They followed a smooth pattern, curving up, then down, like a pendulum. That alone changed the tone of every internal discussion. Because natural motion doesn't echo, it trails, it stumbles, it reacts unpredictably. This did not. Further complicating the model was that Atlas wasn't emitting anything that could affect the twin. There were no gas jets, no dust clouds, no thermal energy that could be transferring momentum. The two objects weren't connected, and yet, one moved, the other followed, consistently. ESA's physics group introduced a term that had only been used in simulations before, non-local orbital mimicry. It describes a situation where one object seems to behave as though it's responding to the positional state of another object, without any known force acting between them. A kind of delayed mirroring. In theory, it's impossible. In practice, it was happening. The phenomenon repeated 6 more times over a 12-hour span. Each time, Atlas would adjust slightly, sometimes from thermal pressure, sometimes from microcourse drift, and each time the twin would follow, but only the twin, not in advance, not with variation, never independently, it never led. That fact became central to a new hypothesis, that the twin wasn't just mimicking, it was tracking, it was watching Atlas, following it, not just in space, but in behavior. One team at the Max Planck Institute noted something chilling in their report. The twin does not act unless Atlas acts. In all other moments, it remains inert. No autonomous variation, no drift. It exists in wait state until prompted. That phrasing, wait state, had never appeared in any prior cometary report. It's a term borrowed from computing, from robotics, from systems that remain idle until called upon to act. But comets don't wait. They erode, they fracture, they wander, they don't echo, and they don't follow with precision timing measured in seconds, unless something is listening, unless something is observing, unless motion is no longer just the result of force, but the result of a choice. Jets are loud, at least in data. When a comet releases a jet, whether it's water vapor, carbon monoxide, or dust, the event registers across multiple instruments. There's a burst of thermal infrared, a spike in volatile emissions, a telltale brightening in visible light, sometimes even a push in trajectory. Scientists have catalogued hundreds of such outbursts, each leaving behind a familiar signature: energy, particles, motion. But what happened on the morning of December 12th was different. There was no flare, no sound, no rise in temperature, just movement. At 0407 UTC, the twin comet, positioned just behind 3I Atlas, experienced a momentary acceleration. It wasn't dramatic. No rotation, no debris, no change in brightness, but its speed increased. Not from a collision, not from gravitational influence, and not from venting. The shift lasted 0.3 seconds. It was enough to raise questions at both the ESA and NASA tracking centers. A velocity change without an external cause defies comet physics. Something had pushed the twin forward, so they checked for the usual suspects. No radiation spike, no magnetic field interference, no micrometeoroid impact. The vacuum around the twin was clean, completely still, and yet the object had moved. That's when the team at JPL ran a high-resolution visual scan using a long baseline optical array. The results were subtle, but unmistakable. A jet, but not like any they'd seen before. It wasn't luminous, it wasn't messy, it didn't leave a visible trail. Instead, it was narrow, concentrated, barely detectable against the background of space. A cone-shaped projection, extending from the lower midsection of the twin, trailing behind it like a knife slice through darkness. Only by stacking 88 frames could the analysts resolve it. But there it was, a silent jet. No outgassing detected, no thermal bloom, just kinetic displacement. The twin had accelerated using a force that left no signature, no heat, no molecules, no light. This forced scientists to reach for a term they'd never used in public documentation on comets: non-volatile kinetic jet. Essentially, movement without mass ejection. In engineering, this would imply propulsion. Not chemical, not ion, but perhaps pressure-based, or even electromagnetic. But such methods don't occur in nature, not without energy input and a system to direct that energy. Yet the twin, silent and inert until then, had moved in a straight, clean line. It had repositioned itself. The implications were immediate. If the object had the ability to accelerate on command, without shedding detectable material, it might not be a comet at all, at least not entirely. It might be masking as one, or it might be something else altogether, something that understands direction, something capable of correcting course. Astronomers began combing through previous footage, looking for other jets they had missed, microbursts that might have occurred during prior approach phases. What they found stunned them further: 2 faint directional lines at opposing intervals, both perfectly aligned with previous shifts in Atlas's path. 3 jets, all perfectly timed, none visible without computational enhancement. The twin wasn't reacting randomly, it was responding, adjusting, holding a formation behind Atlas, not falling into orbit but maintaining one, and doing so with a method completely foreign to current comet science. Scientists stopped calling it a jet. They began calling it a maneuver. And the silence around that decision was louder than any burst of gas. Because the moment a comet maneuvers, without mass, without heat, without light, it stops being a comet and becomes a craft. In orbital mechanics, alignments happen all the time. Moons align with planets, planets align with stars, comets align with gravitational wells. But these alignments are typically the result of scale, of mass, motion, and timing over vast distances. They don't choose. They follow the math. The alignment is incidental, not intentional. But what occurred just hours after the silent jet maneuver was not incidental. It was precise. At 09:11 UTC on December 12th, both 3I Atlas and its trailing twin entered a phase of motion that, when viewed from Earth, formed a perfect linear projection, one directly pointed at our planet. To the naked eye, it meant little. 2 faint specks lost in the background of the inner solar system. But to observatories equipped with high-resolution vector tracking software, the implications were chilling. The twin had shifted position, not just in space, but in angle. It wasn't trailing Atlas passively anymore. It was lining up. A direct Earth vector alignment means that from a fixed observation point on Earth, the twin's forward momentum was now aimed with near-zero deviation at our orbital path. Not drifting, not swinging around the sun, not slingshotting outward. A clean, measured trajectory. This wasn't typical for comets. Even rogue interstellar objects like Oumuamua or Borisov entered and exited our solar system with curved hyperbolic arcs. Their paths were dictated by gravity and solar escape velocity. None of them flew straight. But the twin was flying straight. That alone drew attention. But what made the alignment more disturbing was its timing. Just 31 minutes earlier, 3I Atlas had performed a microcourse adjustment. It was minor, only a fraction of a degree. But once again, the twin followed. And this time, the course correction didn't bring the 2 objects closer together. It pointed them both at Earth. Some called it a coincidence, others didn't. At the European Southern Observatory, a joint task force ran 6 models comparing the twins' new trajectory to known gravitational influences. Mars, Venus, the Sun's pressure zones. None accounted for the realignment. The only constant in every model was Earth. One trajectory, one direction, one solution. Earth. For a full hour, the twin held that alignment with machine-like stability. No wobble, no variance, no decay. It wasn't orbiting, it was closing in. Meanwhile, analysts turned to Doppler radar scans, hoping to detect subtle shifts in velocity as confirmation. What they found made them pause. The twin's velocity curve had flattened. It wasn't accelerating anymore, it was cruising. Objects that coast at constant speed, without gravitational interference, suggest one of 2 things. Either they're inert, or they've already finished their maneuver. And if the twin had already finished its maneuver, the implication was worse than active propulsion. It was targeting. This idea quickly spread among internal research groups. Not in the public documents, not in the press releases, but in encrypted memos and late-night emergency calls. The kind of alignment they were observing was so exact, so symmetrical, and so stable that only one conclusion made sense. It was deliberate. From Mauna Kea to Madrid, the same diagrams were drawn, same vectors, same impact corridor. Not intersecting Earth immediately, but holding an angle that would keep the twin in a stable path toward us, unless deflected. But who would deflect it? And more urgently, who aligned it? The twin hadn't just moved, it hadn't just mimicked, it had settled. Its nose, its vector, its entire energy was now focused, on us. And while Atlas still showed signs of fluctuation and drift, the twin had become a fixed point in motion. A line aimed through silence, through space, through time, straight to Earth. The tail of a comet is its identity. It is how we spot them from Earth, sometimes long before the nucleus comes into view. It's not just a streak of light, it's a signature of interaction between the object and the solar wind, between ancient ice and relentless radiation. When a comet enters the inner solar system, its tail blossoms behind it, pushed by solar pressure, stretching millions of kilometers into space. It is the comet's reaction to the sun. But the twin had no reaction, none at all. For over 3 days, telescopes across the globe had been tracking both 3I Atlas and its trailing twin. Atlas behaved like a known, though peculiar comet, outgassing lightly, forming a faint but measurable tail. It fluctuated depending on its distance from the sun, and its dust profile matched a low-activity nucleus, but the twin, it stayed clean, dead clean, no dust, no plasma, no ion stream, no reactive tail. This silence began to disturb even the most conservative scientists. At first, the explanation was simple. Perhaps it was a rocky interstellar object. Perhaps it had no volatiles to release. But that theory began to fall apart the moment researchers tried to measure its reflectivity. Because there was nothing to reflect. The twin was dark, too dark, so dark that light barely bounced off its surface. Spectroscopy revealed a flat line, less than half the albedo of the darkest known comets. It didn't glow, it didn't flicker, it absorbed almost everything. That alone was suspicious. But what made the data more urgent was the orientation. When comets travel through space, their tails naturally form in opposition to the solar wind, always pointing away from the sun regardless of their direction of motion. But the twin was moving without resistance, without drag, without deflection. It was ignoring the sun. And ignoring the sun means ignoring the very force that shapes every known comet's behavior. The Solar and Heliospheric Observatory, SOHO, ran particle detection scans as the twin crossed a mid-intensity stream of solar wind. Any natural object would have been forced to produce a tail, or at least leave behind a faint trail of ionic displacement. But again, nothing. No energy trail, no ion arc, no tail at all. This wasn't just a dormant comet. It was something else. A body moving through the solar system that didn't shed, didn't erode, didn't bend to the forces of space. It maintained its course with a level of precision that bordered on artificial, and it did so in silence. Then came the modelling problem. With no tail to track, analysts lost one of their key measurement tools, momentum loss. Every active comet can be tracked based on how much material it sheds. That material creates drag. It slows the object, shifts its path slightly over time, but without a tail there was no drag, no trail to measure, and no way to estimate internal decay. In other words, the twin was stable. Too stable. It wasn't breaking apart. It wasn't being torn by gravitational forces. It was holding shape with a consistency that exceeded even dense asteroids. And yet, unlike asteroids, it showed course control. So what was it? NASA quietly revised its internal classification. 3I2 object, tail absent, behavior inconsistent with cometary dynamics. No public release, just a file update. The tail, or lack thereof, had become a statement. This object wasn't shedding history. It wasn't reacting to heat, pressure, or light. It was gliding, deliberate and clean, without leaving a mark behind. And in space, sometimes the most terrifying thing isn't what an object does, it's what it refuses to do. Everything in space has a temperature. Even in the vacuum, even at hundreds of millions of kilometers from the sun, objects radiate. Rocks absorb sunlight and emit infrared. Dust heats up and cools down. Comets flare when they approach the inner solar system, their frozen cores awakening with warmth, outgassing, boiling, vaporizing. That's how we find them. That's how we measure them. Not by sight, by heat. But the twin had none. No warmth, no variation, no trace of thermal activity. When the twin comet crossed into the inner solar system, multiple telescopes switched to infrared to monitor its behavior. The first expectation was minimal heat. After all, many comets only show moderate temperature changes early in their approach. But what was found wasn't minimal. It was non-existent. Zero heat differential. Zero infrared bloom. Just a black object moving through space with a thermal profile so flat, so still, that it may as well have been invisible to heat sensors. At first, the suspicion fell on instrumentation. Maybe the filters were misaligned, maybe calibration was off. But scan after scan, system after system produced the same result. No heat. This placed the twin in a category that shouldn't exist, because even the coldest asteroids, those far beyond Neptune, still produce some thermal signature under solar exposure. But the twin, it passed through a moderate intensity solar wind zone and remained thermally dead. And here's what chilled analysts the most. 3I Atlas, in front of the twin, showed normal thermal behavior. Its outer layer warmed slightly. Its volatile compounds began to activate, as expected. But the twin, just behind it, same exposure, same region, same trajectory, remained untouched. No rise, no reaction, nothing. That asymmetry became critical, because it ruled out solar distance as the explanation. It ruled out shielding, and it ruled out any passive interpretation. The twin wasn't just failing to heat, it was resisting heat. And that doesn't happen naturally. At the Advanced Spaceborne Thermal Emission and Reflection Radiometer, ASTER, a team ran simulations comparing thermal diffusion across various materials: ice, carbon, nickel, iron, basalt. All of them, when exposed to the same environment as the twin, would have responded. The only way to reproduce the twin's profile: insulate the object with a layer designed to reflect or absorb energy without emitting it back. Something engineered, something purposeful. NASA's Goddard Center issued a quiet memo internally. They didn't call it a comet anymore. They called it a non-radiative body with guided motion. The phrase was deliberate. Not a comet, not an asteroid, a body, a guided one, without radiance, and that single reclassification removed it from every known category of solar system object. Because if something can move without shedding heat, if something can glide without reflecting, if something can pass through radiation and remain invisible to temperature, then it is not obeying thermodynamics in the way we understand. And if it's not obeying thermodynamics, it might be controlling it. This opened the door to darker possibilities. Was the twin shielding itself? Cloaking? Emitting heat directionally, away from Earth-based instruments? Or was it something more terrifying? Something so well contained, so perfectly sealed, that not even light or warmth could escape? That would imply structure, a hull, a design. Comets don't have those. Rocks don't reflect radiation without absorbing it first, and nothing natural moves in silence while remaining cold under a burning star. Except this one. The twin had become a thermal ghost, moving, observing, aligning, and never once leaving a trace of heat behind. A presence, gliding through light, completely cold. Objects in space do not reflect radio waves uniformly. Some scatter them, some absorb them. Others bend them based on their density or internal composition. But very few reflect high-frequency radio waves with clarity. That kind of precision only happens under specific conditions, like smooth surfaces, metallic content, or internal symmetry. Which is why, when the twin was illuminated by a pulse of high-frequency radar from the Goldstone Deep Space Complex, what came back was so unexpected. A mirror. That's what the data looked like. A clean, sharp bounce, like radar hitting the surface of a satellite dish. No dispersion, no scattering, just a dense, high-intensity return with minimal signal loss. For comparison, 3I Atlas, just ahead of the twin, produced the expected return signature. Irregular, noisy, varied across its surface. It reflected like an ice-covered rock. But the twin responded like glass-covered steel. Engineers reran the pulse, convinced there had been an error. They changed the angle, adjusted the timing, calibrated for solar wind interference. Nothing changed. The result remained unnervingly clean. Then came the second anomaly. When the radar pulse hit the twin at 8.4 GHz, it not only bounced back with clarity, it seemed to amplify slightly. Technically, that should be impossible. Natural objects can reflect, yes, but amplify? That would require circuitry, a surface geometry capable of focusing incoming energy and returning it in a tighter beam, something akin to a phased array, and that's not found in comets, asteroids, or space debris. Yet that's exactly what the twin did. The bounce-back waveform wasn't just clean, it was narrow, sharply defined, almost too perfect. So perfect, in fact, that one technician noted it looked like the return signature of a geostationary military satellite. But there's no satellite behind 3i Atlas, only the twin, and the twin is not transmitting, it's receiving and responding. That's when suspicion began to grow, around one possibility few wanted to say out loud: structured surfaces. Because for a radio wave to return this way, the reflecting body must be unusually smooth, or intentionally patterned. Both options point to a level of artificiality that goes far beyond frozen rock. So the question was simple. What kind of object can reflect radio waves at high frequencies from multiple angles, while also staying thermally invisible and silent in optical scans? Only one kind, a constructed one. The research team at the Very Large Array, VLA, cross-referenced their own data and found something even more disturbing. Not only had the twin reflected the radar pulse, it had done so with temporal consistency. Over 3 rotations of Earth, the signal return remained unchanged in amplitude and delay, suggesting a stable surface orientation, which meant the object wasn't tumbling, it was holding position, maintaining the same geometry toward Earth across multiple flybys. That's guidance. It also meant the surface in question, whatever material it was made of, was aligned with Earth's position intentionally, or at least reactively. This wasn't passive reflection. It was targeted coherence. By this point, the team had ruled out natural composition. The reflectivity was too uniform, the signal too steady, the angle too clean. It all suggested design, smooth panels or layered skin, the kind seen in high-altitude radar-evading craft. Except this was beyond Earth, and it wasn't made by us. The twin had responded not just with light, or with motion, or with silence. It had responded with signal. And in the world of deep space science, signal is communication, even if it doesn't speak, even if it doesn't decode, even if it says nothing at all. A reflection like that is a message. Light doesn't lie. Even in the deep void of space where distances warp our perception, and timing plays tricks on our instruments, brightness is one of the few signals that remains honest. It reflects surface material, rotation, shadow, distance, and even internal structure. For comets, that light usually flickers, faint, irregular, always dancing in response to volatile bursts, spins, or outgassing. But the twin's light wasn't dancing, it was pulsing, not wildly, not like a flare or explosive vent, but rhythmically. Every 31 seconds, a faint modulation in brightness occurred. At first, it seemed like noise, maybe a calibration issue, a background echo from solar interference, but the rhythm persisted. 31 seconds. Every time. What made it more troubling was the amplitude of the change. Subtle, but deliberate. It didn't spike. It didn't fade. It just shifted. Like a heartbeat. Not enough to trigger panic in public reporting, but enough for internal observatories to tag it as non-natural modulation. This wasn't twinkling from atmospheric interference. This wasn't rotation. This wasn't sunlight bouncing off an irregular surface, because the twin wasn't rotating. It was stable, and yet its light was pulsing. Brightness modulation like this usually implies one of two things. Either an object is changing in its surface reflectivity, such as expanding gas clouds or surface, melting, or it's emitting something under controlled timing. The twin wasn't outgassing, and it wasn't melting, so that left one possibility. The surface was shifting, not breaking apart, not fragmenting, but changing its profile at timed intervals, a kind of surface movement, or worse, internal patterning. This is where the James Webb Space Telescope was brought in. Though it hadn't been trained directly on the twin yet, its wide-field monitors began passively capturing the modulation in the same 31-second interval, even from a lateral view. That confirmed it wasn't a localized phenomenon. It wasn't an Earth-based illusion. It was real, a slow, low-intensity blinking pattern. And the brightness didn't fade completely. It dipped, as if part of the surface was adjusting, then returning, then adjusting again. 31 seconds every time. Researchers at the Max Planck Institute ran Fourier analyses on the light pattern and found something strange. The signal was too clean. No internal chaos, no random scatter, no trailing decay. Natural bodies don't blink like that. They flare, they spike, they tumble, but the twin was signalling. The idea started to form in hushed discussions. What if the brightness wasn't passive? What if it wasn't a reflection at all? What if the twin was emitting? That would change everything. It would suggest that the twin wasn't just reacting to the environment. It was responding to observation, holding position, modulating brightness, reflecting high-frequency radio pulses, emitting no heat, and now blinking, like a beacon, a soft one, barely noticeable, but persistent. The pattern had no known astronomical equivalent, not from binary stars, not from pulsars, not from magnetars or comets or asteroids. It wasn't spinning, it wasn't dying, it was behaving. And the brightness modulation didn't stop after a few hours. It continued into the next day, consistent, clean, timed, just enough to be noticed, just enough to be tracked, but not enough to explain. Because in space, nothing blinks like that unless it wants to be seen, not by accident, and not by nature. If you want to understand a celestial object, you don't wait for it to arrive, you simulate it. Before any close encounter with Earth, observatories and space agencies run millions of predictive models, simulations designed to forecast what will happen as the object nears our planet. These are used to measure orbital deviation, gravitational stress, electromagnetic interaction, and visibility windows. 3i Atlas had already passed through several of these simulations with mixed results, but the twin broke the model. The first attempt to simulate the twin's close pass was made within hours of its discovery, trailing behind Atlas. The assumption was that it followed a nearly identical trajectory. Analysts plugged in the same parameters: speed, angle, density, solar wind resistance, gravitational deflection, and within minutes the system crashed. Not in a dramatic, catastrophic failure, but in a quiet refusal. The model didn't know what to do with the input. Why? Because the twin wasn't behaving like a known object. There was no tail, no mass shedding, no rotation, and most importantly, no drag. Without that drag, the standard model couldn't account for slowdown or solar influence. It simply projected a direct line. Too direct, too perfect. So they tried again. This time, they softened the mass estimate, adjusted the albedo, even introduced microthrust assumptions, tiny bursts of motion that some space debris can produce after internal shifts. Still, the simulation returned one result: controlled glide. That was the phrase embedded in the final frame of the visual output. Not a cometary arc, not a gravitational slingshot, just a clean vector, unbent, untouched, threading between Atlas's curve and Earth's orbital path. That shouldn't happen. Nothing in space glides like that unless it's actively adjusting. Even near-Earth asteroids wobble. Even the most stable satellites drift. But the twin seemed immune to planetary gravity until the moment it wasn't. And when it was affected, it responded with a course correction that defied the algorithm's assumptions. The European Space Operations Centre, ESOC, ran its own simulation, using different input parameters from radar reflection data and brightness modulation patterns. Their result? A near pass, uncomfortably near, not a collision, not even an atmospheric skim, but a pass close enough to fall within what's known as the geokinetic influence boundary, a thin envelope around Earth where electromagnetic effects, if the object carries any charge or emission, could interact with satellites, upper atmosphere layers, or even magnetic fields. That's when the terminology changed. It was no longer labelled a passive flyby. The twin was now officially classed as an anomalous trajectory body with high proximity potential. In simpler terms, it's coming close, and we don't fully understand what that means. More concerning was how late in the simulation timeline the deviation occurred. Atlas, for example, shows orbital drift well in advance, months out. But the twin stayed straight until just a few 100,000 kilometers from Earth's projected location. Then, only then, did it show the tiniest bend, almost like a decision, not a physical one, a navigational one. And that's not how comets work. Comets don't decide when to turn. They drift, they break, they burn. The twin didn't. It held, then it curved, then it held again. The simulation didn't know what to do with that, because motion in space is about force and resistance. But the twin seemed to be responding to proximity itself, like it was aware of Earth's location, and only adjusted once it entered a certain range. By the end of the simulation, one conclusion had become clear. This pass would not be random, it would be measured, and if something is measuring its distance to Earth, it might already know we're watching. Speed is one of the few truths in space that doesn't lie. Once an object is in motion, especially at interstellar or interplanetary scales, it tends to stay in motion, unless something intervenes. Comets and asteroids slow down due to friction, solar wind resistance, gravitational pull, or atmospheric entry. These are predictable forces, measurable and consistent. But the twin didn't follow that logic. Its slowdown wasn't gradual, it was timed, and worse, it was synchronized. On December 12th, 3SI Atlas passed a velocity monitoring checkpoint used by the Deep Space Network. As expected, its speed had dropped slightly due to standard solar drag, nothing unusual. Minutes later, the twin crossed the same point and matched its slowdown. Exactly. Not just in rate, but in pattern. Same curve, same gradient. As if it had mimicked the deceleration of 3I Atlas perfectly. That alone raised eyebrows, but what followed pushed it beyond coincidence. Roughly 12 hours later, a second deceleration window occurred. Atlas dipped again, fractionally slower than before, due to approaching the Earth interaction corridor. A natural dip. But the twin did it again. Same time, same shape, same behavior. It was like watching a shadow learn in real time. That's not how passive objects behave. Even twin comets born of the same origin rarely decelerate in perfect sync. Variations in mass, spin, orientation, and surface structure all introduce noise, tiny deviations in how they respond to external forces. But the twin had no deviation. It moved in tandem. Not only that, it kept its distance constant, not by accident, but seemingly by design. It didn't drift forward. It didn't lag behind. It tracked Atlas with perfect timing, responding to external forces as if tethered, but no tether existed. Scientists at Caltech ran the velocity curves side by side and overlaid the slowdown pattern. They lined up to the second. There was no lead time, no delay. This wasn't one object reacting to another. It was two objects responding to the same signal. Or one object adjusting its behavior to copy the other in real time. And that raised a terrifying hypothesis. What if the twin wasn't natural? What if it was shadowing Atlas? Not gravitationally, but intentionally. Because that level of synchronization doesn't happen by chance. It was too clean, too elegant. Like watching a formation flight at planetary scale. And what's more chilling, it only slowed down when Atlas did. Not when external forces demanded it. The twin could have blazed ahead. Could have ignored the drift. But it didn't. It matched. As if it was studying Atlas. As if it was tracking Earth's response to Atlas. And copying its behavior to stay one step behind detection. That's not a comet. That's not a rock. That's mimicry. And mimicry, especially on this scale, is never accidental. A comet can tumble. A rock can burn. A fragment can shatter. But only something aware, only something built, can slow down in sync with another object that it's following across millions of kilometers, adjusting its speed without any visible cause, fuel, or thrust. This wasn't two comets caught in the same stream. This was a performance, and the twin was playing a role, until it got close enough to no longer pretend. The Doppler effect is one of the oldest and most reliable tools in astronomy. When something moves toward us, its signal compresses. When it moves away, it stretches. This shift, called Doppler drift, is how we measure speed, direction, and even rotational velocity. It works with light, radio waves, and sound across the cosmos. It doesn't fail, but with the twin, it stopped working. When 3i Atlas entered Doppler tracking range, its readings were typical. Its spectral lines shifted just slightly in accordance with its inbound trajectory. As expected, the signals compressed as it neared Earth. Minor fluctuations, normal deviations. Then the twin entered the same Doppler corridor, and the lines froze. At first, observers thought it was a system glitch. Instruments were recalibrated, software reinstalled, dishes retuned, but every check came back clean. No errors, no data loss. The twin's signature was simply not moving, not drifting, not shifting in any way. It wasn't silent, it was broadcasting. But the frequency stayed locked, like it was parked. That's not supposed to happen. Even stable space objects exhibit microdrift, thermal wobble, reflective inconsistencies. Nothing holds a perfectly constant Doppler profile, unless it's artificially correcting itself second by second. The observatories ran a deeper spectral analysis. Instead of chaos, they found symmetry. The twin's return signal didn't stretch or squeeze. It just hovered, as though the object wasn't travelling through space but holding a position within it, bypassing the very fabric of motion. It didn't make sense, but then came the comparison. When engineers overlaid the Doppler data from Atlas and the twin, they expected to see two trajectories converging, one slightly behind the other. But what they saw was one object, Atlas, moving through space, while the other, the twin, seemed anchored not in space, anchored in signal space, like its return frequency was decoupled from its motion, which is, again, impossible, unless something on board was actively stabilizing it. That's when a darker theory emerged, frequency shielding. In experimental aerospace engineering, there's a concept known as spectral cloaking, the ability to manipulate or redirect Doppler reflections so that an object appears still or invisible to tracking systems. The tech is theoretical, and no known Earth agency has deployed it in open space. But that's what the twin was doing. It wasn't invisible, it was statically present. Present in a way that no rock, comet, or natural fragment should be. It didn't accelerate. It didn't decelerate. It just refused to express movement. That wasn't nature. That was a choice. Even more disturbing was that during the brief window where the twin passed behind 3i Atlas in alignment with the Sun, it briefly mirrored Atlas's Doppler drift, perfectly. Same shift, same curve. And then, seconds later, it snapped back to neutral, as if it were testing something, as if it was learning how to appear natural, before returning to its static default. The Doppler drift collapsed again, and has remained collapsed ever since. No known celestial body has ever shown this pattern, because nothing drifts, then undrifts, then holds its frequency constant without motion, except something designed to manipulate its observability. In other words, a ghost object, not silent, not invisible, just out of sync with every physical law we know, and if the twin can choose when to be seen, it can also choose when not to. When an object in space holds still, it's rare. When it holds still in relation to Earth's surface, it's unheard of. Satellites can do it. They're engineered to remain geostationary, orbiting at just the right velocity and altitude to match Earth's rotation. From our perspective, they hover in place above the same point on Earth's surface. But comets don't do that. They move, they tumble, they race across the sky, their position shifting against the star field as Earth turns. That's what makes sky tracking possible, predictable movement against a fixed celestial background. Until the twin stopped. Not completely, not universally, but optically. The first sign came from amateur observatories in South America. As the twin approached visibility range from the southern hemisphere, several observers began reporting a strange phenomenon. The object was not shifting. At first it sounded like an error, bad equipment, misaligned mounts, or misidentification. But when 3 independent observatories confirmed the same thing, it became clear. The twin was holding its visual position relative to Earth's surface. It had entered what scientists began calling optical plate lock. In simple terms, the object remained in the same spot in the sky, despite Earth's rotation. That's not how comets behave. When the planet turns, all objects, stars, planets, and space rocks, appear to move across the sky. The only exceptions are satellites in carefully designed orbits. These require continuous velocity adjustments to maintain position, but the twin wasn't in geostationary orbit. It wasn't even close. Its altitude, speed, and trajectory didn't allow for a stable hover. And yet, night after night, for just under 3 hours, it held its place in the sky as if pinned to a point above the Earth. Then, without warning, it shifted. Not drifted, shifted. By exactly 8 degrees, before holding that new position for another fixed window of time. Observers tracked this movement and noticed a strange pattern. The lock wasn't tied to celestial coordinates. It was tied to terrestrial ones, to regions on Earth's surface. First, over the Pacific, then over Western Australia, then a brief hold near Madagascar. Each position lasted roughly the same amount of time. Each movement was clean. Each pause was deliberate. Optical plate lock isn't just unusual, it's physically implausible for a natural object. It would require real-time adjustments, precise motion damping, and orientation control systems well beyond anything nature provides. This wasn't orbital coincidence. This was targeted stabilization. Some began comparing it to reconnaissance satellites, objects that lock onto specific regions of Earth for imaging or signal monitoring. But those satellites are launched from Earth. We track them. We own them. The twin, we had no origin, no launch, no registration, no engine trails, no fuel signature, and yet it moved like it had a mission. There was no outward propulsion, no heat, no wobble, just cold, quiet, optical stabilization. For many, this was the moment the conversation shifted, from speculation to concern, because orbital mechanics don't allow for spontaneous visual lock without constant corrections. And corrections require intent. This wasn't a comet drifting through a gravitational corridor. This was something observing, studying, locking on, not to stars, not to space, but to Earth. The last known optical plate lock ended just minutes before the twin vanished behind the shadow of 3I Atlas, entering a blind zone that ground-based telescopes couldn't penetrate. And in that moment, it disappeared, not just visually, but spectrally. Like a program finishing its scan, or a system powering down, not random, not chaotic, just done. In space, nothing stays perfectly still. Even the most stable celestial bodies, asteroids, dwarf planets, ancient comets, spin. Rotation is the default. From the moment an object forms, it carries angular momentum. Whether it's from the collision that created it, the gravitational tug of a nearby star, or even uneven outgassing from its surface, spin is nearly universal. It's how we classify motion, how we measure mass, how we predict future trajectory. But the twin didn't spin, at all. As it approached the Earth-Moon corridor, multiple telescopic arrays began monitoring its surface reflectivity. Under standard conditions, as a comet rotates, the intensity of reflected light from the Sun fluctuates, creating rhythmic pulses in data. Atlas had a clean, readable rotation signature. The twin had none. It wasn't just low, it was flatlined. A perfectly even reflectivity curve across hours of observation. No oscillation, no flicker, no shift. That's not just rare, it's deeply unnatural. Initial skepticism led some researchers to suggest that the object's rotation might simply be aligned along the Earth observer axis, meaning it could be spinning, but not in a direction visible to us. But that theory didn't hold up. Multiple observatories, from Chile to Japan, observed the twin from different angles as it passed, creating a triangulated visual analysis. Each one returned the same result: 0 rotational variation. No spin, no tumble, nothing. It was still. The term that quickly spread among scientists was spinless companion. But companion implied more than physical proximity. It implied design. Because without spin, the twin should have been unstable. It should have been tumbling chaotically, disturbed by solar wind and minor gravitational nudges. Instead, it remained fixed in orientation. This presented an even deeper mystery. How was it maintaining its posture? To stay motionless in space, especially while moving at high velocity near a planetary body, requires an immense amount of real-time correction. Tiny vector changes, torque adjustments, energy management. But the twin had no visible mechanism, no jets, no flares, no signature, just silence, That's when a new theory emerged. Not that the object lacked spin, but that it was actively suppressing it. In aerospace terms, we call it inertial damping, the ability to resist rotational momentum using internal mass redistribution or gyroscopic balance. Only our most advanced spacecraft can attempt such feats, and even then, only for short durations. But the twin had been spinless for days, holding its frame perfectly, facing Earth in every visible exposure. It didn't rotate around the sun. It didn't tumble through space. It pointed, intentionally, like a dish, like a sensor. That's not a natural object, it's a platform, and the implications are staggering. If it wasn't tumbling, it wasn't aging in the way comets do. If it wasn't spinning, it wasn't shedding heat, or redistributing impact forces or revealing internal structure. It was hiding, not in shadow, but in stillness, as if it knew that motion reveals intent, and by removing motion altogether, it became harder to categorize. Not a comet, not an asteroid, just a shape in the void, still, watching, following, and entirely unwilling to turn away. Solar flares are brute force events. They erupt from the sun's surface without warning, massive bursts of charged particles, electromagnetic radiation, and heat. When one is directed toward Earth or any object in its path, we expect a chain reaction. Auroras light up, satellites switch to safe mode, communications scramble, and in some cases power grids take a hit. But in space, the response is even more predictable. Comets react violently. The sudden blast of solar wind forces outgassing, tears at tails, and alters trajectories. Dust particles scatter, ion tails shift direction. Comets are fragile, and flares expose their instability. On the morning of December 12th, the Sun released a moderate flare, category M. Not enough to panic, but enough to register across the solar system. Earth's magnetosphere responded as expected. Aurora alerts were issued. Several satellites preemptively powered down. 3i Atlas showed a visible reaction within 40 minutes. Its ion trail shimmered, expanded, and briefly curved as it absorbed the energy blast. Standard comet behavior, predictable physics. Then came the twin. Or rather, no reaction came. Nothing moved, nothing expanded. Its structure, whatever it was, remained exactly as it had been. Observers ran thermal overlays, no heat absorption, no radiation bounce back, no shift in electromagnetic profile. Even non-reflective bodies warm under a solar flare. Even rocks glow faintly in infrared. But the twin showed nothing. Either it had absorbed the entire flare without heating up, or it deflected it entirely. That's when the optical data came in. For 7 seconds during peak flare exposure, the twin silhouette brightened. Not by much, but enough to register a smooth geometric pulse. It wasn't light scatter, it wasn't heat shimmer, it was structured response. Some compared it to phased array panels, surfaces used on advanced spacecraft to dynamically adjust to incoming signals, not with brute force, but with controlled reconfiguration of surface properties. In other words, not just shielding, adaptive shielding. As if the object had anticipated the flare, as if it had turned itself into a reflector or a sponge. Not only did it resist being pushed off course, it absorbed energy without effect, or worse, converted it. This possibility triggered intense debate. Was the twin passively immune, or actively feeding? Because a solar flare delivers raw energy. If an object could harness even a fraction of that, it would power systems for days, weeks, or longer. What we saw that morning wasn't just a mystery. It was a mechanical response dressed in silence. No comet behaves like that. Even metal-rich asteroids experience heating and radiative drift under flare conditions. The twin remained constant. Constant shape, constant temperature, constant silence. It wasn't resisting the flare, it was engaging with it, on terms we don't yet understand. Imagine throwing a wave at a wall and the wall doesn't move, but subtly reshapes its surface to cancel the wave entirely. That's what happened, and as quickly as the flare hit, the moment passed. Atlas continued its altered drift. The twin returned to shadow. No residue, no signal, just the memory of a response. And in that moment, a terrifying thought emerged across observatories. If it reacts to energy this intelligently, what does it do with it? Because no known object passively resists a solar flare, and certainly not with such quiet elegance. This wasn't a survivor, it was a participant, and that makes it something else entirely. For weeks, 3i Atlas had been the primary concern. It was fast, it was massive, it had crossed the sun without disintegrating, and its trajectory was too close to Earth to be ignored. Observatories around the world had zeroed in on it, mapping every rotation, flare, and course correction. It was the headline object, until the twin began to move first. At first, it was subtle. The assumption had always been that the twin was trailing, following Atlas in the same corridor, perhaps even debris from the same origin, a fragment, a passenger, or some kind of mimicking shadow. But then, early on December 12th, the models diverged. The orbital path of Atlas remained consistent, but the twin changed. Its velocity increased, not dramatically, but in a way that shifted the center of the system. Trajectory overlays revealed that it was no longer a follower, it had become a guide. Atlas, still visible, began to drift into a new pattern, one that traced the same arc the twin had already completed minutes earlier. Analysts at 2 independent tracking stations saw the same thing. The path of Atlas was adjusting ever so slightly to align with the vector established by the twin. That wasn't coincidence. That was a lead-follow dynamic. In physics, when one object passively trails another, we expect gravitational influence. But here, Atlas had more mass. It should have influenced the twin, not the other way around. So how was Atlas now tracing the twin's path? Some suggested micro-interference, others proposed particle field tethering. But a more troubling theory gained ground quickly: behavioral mimicry. Not from the twin, but from Atlas itself. Had Atlas been autonomous all along? Was it reacting, learning? Because when a comet follows a lead object into a curve, with timing that falls outside gravitational lag, it's adapting, it's syncing, it's trusting the path ahead, as if the twin knew something, as if it had gone first, for a reason. The twin's movement became more aggressive. Its arc tightened, its alignment with Earth's orbital plane improved by less than half a degree, but enough to raise concern, because Atlas followed that same correction within minutes. What we were watching wasn't 2 comets in a shared orbit. We were watching a system, one that coordinated movement, one that established leadership and mirrored behavior. Cometary bodies don't do this. They don't communicate, they don't share vectors, they don't take turns leading. But here they were, 2 separate masses, one reacting, one anticipating, and both adjusting course toward the same planetary intersection. That's not physics, that's strategy, and it reframed everything we thought we knew. Atlas was not simply the active anomaly, it was being guided. The twin wasn't debris, it wasn't a fragment, it was the primary, and whatever these 2 were, they were in coordination, maybe not through signal, maybe not through force, but through behavior. A pair with purpose, and the one that spoke the loudest was the quiet one, the one without heat, without spin, without signature, the one that led with emotion and waited to be followed. That's not chaos, that's command. And for the first time since tracking began, 3i Atlas was no longer the most frightening object in the sky, because the thing it was listening to was already here. By the time Earth rotated beneath the projected intersection point, the sky had already quieted, not in the poetic sense, in the literal one. On the night of December the 12th, just after the twin made its final course correction and Atlas followed suit, something else happened. Something that ground-based sensors began reporting within hours. A drop in background noise. Not sound, as in what our ears register, but electromagnetic noise. The natural hum of the planet's upper atmosphere, normally filled with solar radiation, reflected particles and low-frequency waves. It was gone. Radio astronomers first noticed it when several VLF, very low-frequency, receivers across the southern hemisphere began returning flatlines. These instruments, designed to pick up background space weather, suddenly had nothing to report. No pops, no hiss, no pulse, just a clean sheet of silence. At first it was written off as a solar interference issue. Maybe the recent flare had overloaded or blanked the detectors. But then magnetometers joined the silence, and ionospheric radar scans showed unusually smooth returns, like the high-altitude plasma layer had settled. It hadn't been this quiet in years. Even aurora monitors registered only residual movement, faint and slow. Something had dampened Earth's energetic envelope, and the only new variable in that moment was overhead. Both Atlas and its twin had passed into the near-Earth corridor, just outside orbital range. They weren't entering the atmosphere, they weren't crashing, but they had aligned, not just with each other, but with Earth's magnetic geometry. Satellites didn't go down, power grids held. But above all of it, the silence grew. Astronomers turned their attention to the infrared arrays, hoping to see something, anything, breaking the stillness. But the arrays returned flat as well. No thermal bloom, no trailing heat signature, just absence. It was like the sky had been muted. One researcher called it an electromagnetic blank slate. Another referred to it as earthbound silence. It was a strange term, but it captured the tension perfectly. Because this wasn't silence as peace, it was silence as preparation. Something had arrived, and it had quieted the stage. When space goes silent, it means one of two things. Either something has absorbed the energy, or something has replaced it. But nothing natural replaces Earth's upper atmosphere hum. Not solar storms, not orbital debris, not even deep space probes. What does, however, is shielding, or masking, or intentional suppression. Some hypothesized a kind of electromagnetic soft bubble, something that moved with the twin, neutralizing, frequencies around it. Others proposed active jamming, an unknown object simply silencing the region it occupied. But to do that at planetary scale, that's not stealth, that's authority. Because you don't silence Earth's upper atmosphere unless you're doing something you don't want detected. And Earth had gone quiet just as both objects settled into alignment. The twin led, Atlas followed, and Earth went still. It wasn't a sound we heard, it was a sound we didn't. And every missing frequency, every flattened radar return, every silent aurora swirl, was saying the same thing. Something had arrived. It wasn't declaring itself. It wasn't announcing its intent. It was simply here, with no tail, no spin, no voice, only a stillness that spread from sky to soil, a stillness that grew heavier by the hour, until even the wind felt like it was holding its breath.